chapter 5, where we're going to talk about transformations of pairs of random variables, where specifically we're going to talk about finding a PDF of the sum of two independent random variables. So let's assume we have x and y as random variables, and the sum of these two random variables is given by z. So z is equal x plus y. Then the joint characteristic function for x and y, or for z, is given in equation 1, which is the expected value of the exponential of j omega z, where you can go back to previous lecture and find it. But since x and y are independent, we're going to assume that x and y are independent of each other. Then what we can do, we can find the characteristic function for each one of them separately. So the characteristic function for x and then y, and multiply them by each other, and that would be the characteristic function of z. And then what we can do, we can find the PDF for each one of them separately by using the characteristic function approach, as we learned back in chapter 3 for x and y, and then multiply them by each other. That would be the PDF. Another way to find it is by using the convolution approach. Okay. Sorry. As you can see here, the convolution approach is given in equation 6. So if we need to find the PDF of z, so you will take the convolution of the PDF of x times the PDF of x and the PDF of y in terms of z. Okay, and because if they are independent, okay, this is true for if x and y are independent, and this one can be written in this approach right here. Okay, so this convolution can be written by taking the integration of f of x for z minus y times f of y for f of y, okay, from minus infinity to infinity. So this is basically, of course, this is nothing new to you. You've seen the convolution when we took to EE 260 signals and systems. So this is nothing new to you. So, but basically, this is just to refresh your memory. So the convolution for for x and y will be written in this fashion. Now, let's take just an example to show you how to do it by using the convolution approach. Okay, so you can do it like I said, by doing it separately and find the fx by taking the inverse as shown in equation 5. This is the inverse of the characteristic function, and of course we learned that back in chapter 3. Okay. Now let's say we have two PDFs, the PDF for x and y, and these x and y's are independent, okay, as shown in equation 8 and 9. And we need to find the PDF for z, where z is equal x plus y, okay? Again, like I said, you can find the characteristic function for each one of them, or multiply them by each other, okay? And let's say here we want to use the characteristic. We want to use this approach right here, the inverse, the convolution inverse. Okay, so the convolution inverse by using this equation right here, equation 7. Okay, you take the first one right here. So it's going to be, of course, a and b are constant. Both of them are constant, so they'll be out of the integration. And then the expected value minus a, z minus y, times the expected value minus by, of course. And of course, this is, we have step function u of x, and this is u of u. X is going to be z minus u, okay? So now, of course, this one here, since, of course, both of them, since both PDFs are step functions, so most likely, or definitely the PDF, it's going to be larger, 0 or larger. Okay, it's not going to be negative since both of them are larger. Okay, so it's going to be start from Z. But by looking at this unit step Z minus U, okay, of course, if U is equal to Z, it's going to be 0. Okay, the unit step is going to be 1, right? But if U larger than Z, so it's going to be 0. So that's why the integration is going to be from 0 to Z, from 0 to Z. And we do the integration like is shown here. Of course, this is going to be out, okay, or Z going to be out rather, okay. And we do the integration as you can see here, okay. And after you do that, this is a straightforward integration. So this is the end result. This is, we assume that A and B are not equal, because if the A and B are equal, we're going to end up with something different. If A and B are equal, then you go back to equation 12 and redo the integration, okay? Because this one's going to be 0, of course. And if it's 0, I mean, A minus B is going to be equal 0. So it's going to be, this is going to be 1. So the integration, the result of the integration is going to be some equation 14. So we have two cases here. The case number 1, when A is not equal to B, these two constant. Okay. Of course, if they are equal, somebody may say, well, we already have the result here, equation 13. Of course, if they are equal, then we're going to have an infinity. We're going to have a problem. But if they are equal, really, you have to go back to equation 12 and redo the integration, okay? And by redoing the integration, there's nothing to it. This is going to be, like I said, this is going to be 1, and you just do the integration from 0 to Z for du, and the end result will be right here. So you have these two cases. So this is, like I said, this is a simple example on how to use the convolution approach. All right. And now if we have a function, if we have a PDF of functions of two independent random variables where the function is g, x of y, then obviously we will find the, like we said here, we just find the integration for this one. Sorry, we'll find the joint PDF for the joint characteristic function, just like we learned last lecture, which is this lecture right here, okay? And then after that, we just take the inverse. This one is a bit complicated because you have to use some tables, so we're not going to go through it a lot. I mean, this is the easiest one here. By my saying here is that we're just going to focus on the functions where we have x and y are independent, because they are easy, a lot easier to deal with, okay? Okay. The next topic we're going to talk about today, if we have two random variables, x and y, and we created two new random variables in terms of x and y. So we have v is equal g1 and w is equal g2, and both of them are in terms of x and y. So how we're going to find the joint PDF for v and w? Okay, so we're gonna go through this one quickly. You can do it in two ways. Okay, the first one, you will find the joint PDF of v and w is equal to the joint PDF of x and y times the Jacobian of the inverse transformation. Okay, the Jacobian of the inverse of transformation. Okay, or you can say you take the joint PDF of x and y. Of course, joint PDF will have to be given to you, or you need to find it. Okay, if it's not there, and we learn how to find the joint PDF, and you divide it by the Jacobian of the transformation. The Jacobian of the transformation. Now, the two new things here. Now, what's the Jacobian of the transformation? The Jacobian of the transformation is by taking the partial derivative of it's basically it's a matrix, as you can see here, as shown in equation 5. So you need to find either this one or this one. Okay, you didn't have to find both, right? If you decided to use the Jacobian of transformation, you just find this matrix, or if you decided to find the Jacobian of the inverse of the transformation, you find this one. Now, of course, it's all coming from these two functions. So the first one here, we take the partial derivative of v with respect to x. Of course, this is the determinant, and this is v with respect to y, and then partial derivative of w with respect to x, and partial derivative of y with respect to w with respect to y. Okay, and of course, once you have the matrix, you can find the Jacobian x and y. As you can see, this times this minus this times this. We all know how to do that. This is the determinant. Okay, and of course, if you need to find the inverse transformation, of course, you need to find, before you do that, you have to find x, which is the inverse of v, and the inverse of w, x and y. Okay, you need to find x and y from equation 1, and x and y from equation 2, and then you can find the inverse transformation by the same way. So you will take the first derivative. By the way, this is the partial derivative. The first derivative with respect to x, and the partial derivative of x with respect to v, the partial derivative of y with respect to v, and so on and so forth. Okay, so both approaches are valid. So it doesn't matter. Okay, whatever easy for you. Okay, this is just basically explaining what the Jacobian. This is magnitude. We take the magnitude of the Jacobian. Okay, if it's negative, obviously it's going to be positive. So let's take a simple example to explain this one is a little bit better. Equation 2, page 2. So let's say we have two functions, y1 and y2. y1 in terms of x1 and x2, and also y2 is in terms of x1 and x2. The only difference is they have two constants here, a and b, and c and d. Okay, so all of these are constant. Now we need to find, we decided to find the inverse Jacobian matrix. Okay, so by doing that, we need to find, of course, if we need to find this matrix right here, okay, it's very straightforward. You just take the integration with respect to x1 and x2, just like this one here. This is with respect to x and y, x1, x2, and y1, y2. Okay, but let's find the inverse function of x1 and x2. So the inverse function of this one here for x1 in terms of x1, after we all know how to do that. This is x1 is going to be dy1 minus by2 divided by ad minus bc. Okay, and do the same thing for x2. So you need to find x1 and x2 in terms of y1 and y2. These are the inverse x and y. And once you find that, then all you have to do just take the partial derivative of x with respect to y1, and then with respect to y2, and you set them here in equation 4, or equation 14 rather, or this is 11, sorry. And then the partial derivative of x2 with respect to y1, and then with respect to y2. So after you plug in the information, okay, after you do the partial derivative, the end results will be here. You can try it yourself, okay? And after you multiply them by each other, this time, this, okay? We all know how to deal with matrices. And it's going to be 1 over AD minus BC. So, of course, according to this equation, we're going to use this equation 3, since we found the matrix, which is the inverse transformation, the Jacobian of the inverse transformation. So it's going to be the joint PDF of x1 and x2 times the inverse function, the Jacobian of the inverse transformation, y1 and y2. Okay. So this one here, you replace x1 and x2 with these functions right here. Okay, given that the joint PDF is already there. Okay. So you just replace x1 with this function, equation 9, and x2 with this equation, and you multiply by 1 over d minus bd, and that will be the end result. Of course, if we have numbers, obviously the results will be a little bit different. And that's all I have for today's lecture, and actually for chapter 5. So that will be the end of chapter 5. So chapter 5, what we covered today, we covered 2 important things. How we find the PDF of the sum of 2 independent random variables, x and y. Like I said, we can find them in 2 approaches. The first approach by using the characteristic function. Since they are independent, we just find the PDF separately. And the other one, we can use the convolution, okay? The convolution approach, and we had an example on this. And also, if we have 2 functions in terms of 2, let's say if we have a function of, if we have a random variable of a function in terms of x and y, and you use the Jacobian approach, okay? And we have 2 ways to do it. And that's all I have. Do you guys have any questions as far as today's lecture? Okay. If you didn't have any questions, like I said, this is the end of chapter 5. Inshallah, on Sunday, we'll begin with a new material, chapter 6, but it's not going to be included in the quiz. Of course, the quiz, like I said, most likely it's going to be based on some request will be on Sunday, not this coming Sunday, the following Sunday. But I will send you a note on that. يعني مش راح بعد ما نتأكد إنه راح يكون Sunday. Most likely راح يكون خلال فترة المحاضرات عشان ما يكونش في أي تعارض. Okay. If you don't have any questions, I will talk to you inshallah on Sunday. يعطيكم ألف عافية.
يعطيك العافية دكتور.
Okay, شكرا.